Okay, so thank you for introduction. So I'm Sasaki, and so this talk is Cryptanalysis of reduced NORX. And the first I want to say that the research was initially discussed at ASK 2016. So I want to thank the organizer of the conference and attendees of this workshop. And personally, I'm one of the co-authors. Sorry, ASK 2015. I'm sorry. And personally, I'm the co-chairs of ASK 2016, which will be held at Nagoya, as Ted reported last night. And I hope everyone will come to the ASK workshop next year, and we will have some constructive results. Okay, so that was advertisement. Okay, so what we did. So NORX is one of 29 second-round candidates in CSER. And the previous results is not so many. So there's one full distinction for permutation, but this is just for permutation without any key. And so in this research, we studied meaningful security notions for reduced rounds in the Nonce-Respect setting. So we tried two approaches. One is guess and determine, and another is internal difference. And the result is, so we could break half of the full rounds, half rounds, 2 out of 4 rounds. And we also proposed key stream distinction with practical complexity. So this is the introduction of NORX. So NORX is sponge or precisely duplex-based AE design, which was designed by Olmasson, Jovanovic, and Neves. It has 2 members, so big NORX and the small NORX. And the state size, so it's sponge. So the state size is 16 words. So for example, 1024 bits for NORX 64. And rate is 3/4 of the state. And the capacity is 1/4 of the state. And the security is 4 words. That means 256 bits for big NORX and 128 for small NORX. And another interesting thing for NORX is it specifies a parallel mode. So the state is duplicated in the top and bottom and make distinct 2 lanes by XORing some constant. And then the messages can be parallelly processed. Okay, so here is initial state, and then the core permutation is computed. So I will explain those parts. So first, state is initialized by key and nonce. So I don't explain details, but it's just initialization. And each round of F, core permutation, so applies 4 forward bit permutation called G. So the 16 words are loaded into the 4x4 word state. And then each round consists of 2 steps. First one is column step. So it applies forward bit permutation for each column. And then after that, diagonal step is computed. That the same permutation is applied in the diagonal forwards. And the number of round is it's actually given as design parameters. And according to the designer's recommended parameters, the number of rounds is 4 or 6. And the primary recommendation is 4 rounds. And actually, we are targeting 4 rounds. Okay, so I will explain G function. So G function looks like this. So the input is 4 words and output is 4 words. And it consists of just bitwise OR, exclusive OR, left shift, and the right rotation, so which is very efficient, especially in the software. And so this computation, which appears 4 times, is called H, and which is an approximation of addition. So it's very interesting design. Okay, so the last thing I want to show, I want to say about design is the design tweak in version 2. So in the previous version, the rate is 10 words and the capacity is 6 words. And then in the NORX version 2, the designers is a bit more, the design is a bit more aggressive, and the rate is 12 watts, and the capacity is 4 watts. And so we observed that now the capacity size and the security size are the same. So that means, so if you recover just a single bit of capacity, then you immediately get key recovery attack. So actually, so our goal in this talk is recovering some bits in the capacity. Okay, so first, we studied some properties of round functions, so I want to explain some of them. So this is a round function, I mean G function. And so diffusion is weaker in backwards than forwards. But actually, so this property has been known in the ancestor of NORX design. So we want to invert the G function first. Okay. So I mean, this part is easily inverted. But the problem, some tricky thing is here. So how to convert H inverse, so which is written in the big figure here. So x prime and y are given, and you need to get x. And due to the this component, it's not so straightforward, but you can recover it efficiently bit by bit. So because this is the shift, the LSB of the state after the shift is 0. So that means you can recover x in the LSB. If you recover LSB, then it gives some information for the second LSB. And so by repeating this, you can get x like bit by bit. So eventually, from given output of G, you can impart the G and can get input to the G. So this is example of like a really basic property. So suppose that B prime, C prime, and D prime are known. I mean, 3 bars are known. Then you can immediately compute B very simply. Or I don't have figures, but I mean C can be computed from given A prime, C prime, D prime. Now actually for the word level analysis, only those two properties can be obtained. But the question is, any other useful properties exist? Okay, so then let's summarize, let's consider the attack scenario. So because NORX is sponge-based, the rate values can be observed from the key stream. Okay, so those 12 words are known. And then the attacker can first guess some bits in the capacity. Remember that winning just one bit is enough to make some varied attack. So we did this analysis. Analysis for any of one of A prime, B prime, C prime, D prime is partially known, and the other 3 are free known. Okay, so I want to show one example here. So A prime, B prime, C prime are free known, and T bits of D prime are known. So we want to discuss like how many bits we can know at the input. Okay, so like this part is again very simple, just it's X4 and rotation. And this part is the new thing that the output of Y is just partially known. And this can be analyzed in 2 cases. The first one is known bits start from LSB, and another is known bits start from middle bits. But this case is exactly the same as the previous one. So you can get the LSB of this state, then it gives you the LSB of x, and this can be iterated up to t bits. So like t bits of x can be recovered. And if t bits start from the middle, so you can get the LSB. But you still can guess this 1 bit. And according to the guess, you can recover the other t bits. So by just paying the cost for 1 bit guess, then you can still recover the t bits. Okay, so at this stage, the known bit position of t and t are the same. But unfortunately, you have some rotation here, so the known bit positions will will differ. So in the second analysis, the number of known bits will be reduced, and then eventually you will lose all the information. But for several rounds, you have some bits. So actually, so this is a like property we had in the paper, and it's saying that from this situation, like t minus R2 and t bits can be recovered. And yeah, we gave 9 properties and several more extensions. And I don't explain details here, but so if you are interested, please see the paper. Okay, so by using those properties, I want to explain some talks. So first one is guess and determine. And so this works both serial and parallel modes. So we don't have to use the parallel mode. And the overall framework is similar to guess and determine attack against the fittest proposed by Dinua and John. So in this, the overview is, so first, observing a key stream in 2 consecutive blocks. So observing key stream here, which gives you 12 words knowledge. And this one gives you another 12 words knowledge. And then we get some capacity values and propagate values through F and try to find some match to check the validity of the guess. Okay, so those 2 states is now appear in the beginning and the end. So this is 2-round permutation. So our strategy is guessing almost all bits of the capacity here. So 3 was a free guessed, and this was partially guessed. And we try to propagate those values in the backward by using the properties I summarized in several pages before. So because like 3 diagonals are free known, that 3 diagonals are free known after the diagonal step. And so this makes 1 diagonal partially known, and then the column step is computed. From like known B, C, D, you can immediately compute B. And so even after column step, you still have some, you still keep some free known words. And the interesting thing is, so considering next is diagonal, the free known words are located in the same diagonal. So you can imagine that after 1 more diagonal step, the attacker can keep some knowledge. And we also try to propagate the input value in forwards, but forward propagation is much stronger than backward propagation, so we can only do 0.5 rounds, I mean, bypassing a column step. And then we want to match, but unfortunately, no bits can be matched directly, so we need something more. Okay, so we traced the linearity of state bits. So now each bit is classified into 3 categories. One is just known, one is unknown, and another is linearly represented by several bits. And in the middle of the matching, some unknown thing might disappear. And this enables us to match some bits. So we developed a tool for the match of a linear relation, and finally succeeded the attack in 2 rounds. So this is the overview, rough idea for guess and determine. Okay, so then I want to explain the idea for internal differential attack. So one is 2-round key recovery, and another is 2-round practical key stream distinction. Okay, so this is like a general slide. So differential, so we want to apply differential attack, but differential attack is generally hard to apply in the Nonce-Respect. But in last year, John and myself and Juan exploited difference between 2 blocks in the analysis on silver authenticated encryption, which is fully parallelizable. So its structure is written like this. So the block computation is related to nonce. So if you change nonce, then the computation becomes completely random, so it's hard to exploit the differential property. So for this thing, we just use single query in the same nonce, of course, and one nonce, of course, and then try to exploit the difference in different blocks. So we wanted to apply this idea to NORX. However, sponge is serial, so no internal difference exists. But the good thing is NORX supports the parallel mode. So actually, the state is duplicated, and then the lane ID is XOR, but ID is just a counter. So ID 1 is simply integer 1, and ID 2 is simply integer 2. And yeah, for some lane IDs, so difference is just Hamming weight 1, and this allows us to consider a difference between two lanes. So here we have difference, and then we can observe like lane rate values after the f in two lanes. So we continue the analysis. Okay, so in this attack, so we make the differential trail for one round, and then we append one round backward computation for key recovery. So covering 2 rounds in total. Okay, so in the forward direction, lane IDs are injected to the second column and the last row, so here. So it's fixed. And so we want to propagate in forward, and we experimentally found that the best characteristic. And after that, we also try some differential probability. And actually, so this is a probability of differential, but just for one round, the probability is quite high. Okay, so then we append a key recovery for the last one round. So this is lane 0, and this is lane 1. And the 12 words can be observed from the key stream. And similarly to guess and determine, we guess secret value, capacity of 2 lanes. So like 3 words are free guessed, and 1 word is partially guessed. But we have some difficulties here. So imagine the classical differential cryptanalysis against block ciphers. Then the secret is key, and which is identical in 2 values in the pair. So if you want to attack block cipher, what you need is just guessing a single key. But here, secret is capacity, and the capacity word are completely different for lane 0 and lane 1. So you need to guess like double bits of the secret, and which is really problematic. And here, we introduce meet in the middle like matching procedure. So that means, so we first analyze lane 0. So we guess nearly close to the exhaustive search cost, and then going back up to here and store the values in the table. And independently, we do the same analysis for lane 1 and matching the difference here. And then this procedure allows to keep the attack complexity low. And so I don't explain the details, but so this is the basic idea for internal differential attack. And the last one is internal differential linear attack. So this is internal differential version of differential linear attack. So the idea is the input difference is fixed. So for the fixed difference, some bits do have difference more likely than other bits, or don't have difference more likely than other bits. So we want to exploit this bias. Now I think usually the differential linear attack constructs some characteristic, but in this research, we verified its bias of output difference experimentally instead of theoretically building a characteristic. And actually, so here is the result. So the horizontal bias, horizontal axis shows the bit positions, and the vertical axis shows the bias that that bit has a difference. So as you can see that some bits tend to have difference more likely than other bits, or some bits would not have a difference compared to other bits. And actually, by using 90 message blocks, we can distinguish the two-round NORX with success probability 97.7%, so which is high. Okay, so I want to conclude my talk. So in this research, we studied meaningful security notions of reduced NORX in the Nonce-Respect setting. And so parallel mode is not exactly the same as serial mode. So we think further investigation seems very interesting in the parallel mode of sponge. So thank you for your attention.